Welcome, this is lecture number 38. In this lecture, we are going to talk about design of current mode control in a buck converter and Matlab based model validation. So, in this lecture, we are going to first summarize different modeling techniques under current mode control. Then we need to validate small signal model using transient simulation, Matlab AC transient simulation. Here we want to validate the closed loop converter. Then after that we will make assessment, like what are the design technique, what are the recommendation, which model to be used for design of current mode control. Then we want to identify loop shaping objective and design of current mode control using simplified small signal model. And finally, the recommendation of design of current mode control design methodology. So, if we look at the very first, I think in week 6 in the model development, we have considered, I think it is week 6, we talked about simplified model of under current mode control with closed current loop, where we have considered the approximation that our average inductor current is approximately equal to control current. That was our approximation, and with this approximation we got very simplified model, and the output impedance looks like this, which consisting, because for a buck converter inductor is in the output side, so inductor can be replaced by a control current source. And then if we want to find out output impedance, then we need to output impedance. If we want to find out output impedance, then it is nothing but minus V0 tilde by I0 tilde, where we want to take IC tilde to be 0, right, that we obtain. And this actually using this we got the output impedance to be it has one ESR 0, which is 1 by RC into C, that is the ESR. Then one pole, in fact this pole should be more accurate pole, it should be, in fact it should be one in more accurate sense, R into RC comma C, because we have ignored the RC. So, that means, let me write again, omega P is equal to 1 by R plus RC into C. But if load resistance is higher than ESR, which is generally the case, then it can be approximated as 1 by RC. And one observation, that means this is output impedance, and which looks like a first order system, like unlike in voltage mode control where we have second order denominator polynomial, but here it is only first order and with an ESR 0. And if we take the control to output transfer function, in that case, in this case what we are considering, GVC, which is nothing but V0 tilde by IC tilde by setting the external load perturbation to be 0. And again this is same as the output impedance under first order model. And so first order model, these two are same, and the DC gain, if we take the control to output transfer function, the DC gain means if we put S equal to j omega and omega equal to 0, then it is simply the load resistance. That means here the DC gain is load dependent, and if we recall in voltage mode control, our control to output transfer function has an input voltage term, and the DC gain was input voltage dependent, and we can reduce, or it can in fact make the DC loop gain independent of input voltage by incorporating input voltage feed forward. Here our DC gain is load resistance dependent, and this will lead to poor load regulation. In case of voltage mode control, your line regulation is poor, here load regulation will be poor, and this can be anticipated by considering load current feed forward, and that also we are going to discuss. Now, one of the major advantage in this current mode control, that your double pole in case of voltage mode control or direct duty ratio control is transformed into a first order pole, but this is an approximate transfer function, because here we have ignored the dynamics of the inductor, because we are assuming the inductor dynamics to be much faster. So, that can be approximated like just like a capacitor RC, the pole due to the RC network. So, that means this is a first order pole, and this can gives us very robust compensation, because earlier we faced difficulty when you have a double pole. It was even very difficult to compensate. Even the exact pole zero cancellation was not sufficient when we are operating under light load or maybe higher load resistance value. Then actual circuit we saw oscillatory behavior where our model response was perfectly fine. So, because that was due to the poor damping into the actual switching converter. But since we have closed the current loop, so it virtually looks like a fast order system. So, it can be, the compensation become much more robust. So, there is no double pole effect, neither there is any Q peaking. Now, this is the first order model, and this first order model we also saw GVG, that means audio susceptibility was 0, because in this model there is no input voltage perturbation term is not there, it is not there in this model. But in actual converter, we know in under current mode control, the audio susceptibility is excellent. That means even if you make a large change in supply voltage, there will be almost no change in the output voltage. It's very excellent line regulation as well as excellent supply transient response. But in approximate model, it shows 0, but there will be slight effect, very almost insignificant effect. But in order to improve the accuracy of the model, then we have discussed that earlier we have considered in method 1, in approximate method, what we have considered? Approximate method, we have considered that IL average was approximately equal to IC average, right? But now we are not considering IL average equal to IC average. So, we are considering some information of duty ratio as well as ripple, but not exactly ripple information, but slope due to the ripple also want to consider. So, there are two methods to do that. If you look at, so this is a Middlebrook method where if we consider this is my actual current, control current, which is coming out of the voltage controller, then we are considering a compensating ramp. That means if you recall that our original current loop, this was our control current and this was our inductor current and this is a comparator, then it goes to our RS latch and this is my Q. So, here we took clock because it is trailing edge modulation. So, in this case we have considered that inductor current is directly compared with the peak current, and then if you want to reset that, if the inductor current goes above peak current, then the comparator will reset the latch circuit. Now, in this case what we are doing, instead of adding the controller voltage directly, we are considering an additional block. That means IC is there, which is my output of the voltage controller, but in addition to that we are considering a ramp compensation, and this ramp either, that means is like a sawtooth waveform, and this is with a slope of MC. So, this is my ramp compensation, and this is generally subtracted from the peak current or it is added with the inductor current. So, the both are identical. So, in this case the waveform shows that you have a dotted line which is a pure current, that means this is the, I am talking about this part, here is the control current. Now, we have subtracted the ramp current. So, the actual current reference, that means if I take this particular term, this waveform is going down because your ramp is subtracted, so its slope will be falling, but actual ramp is rising slope. And this is compared to the inductor current. So, you can see the inductor current is rising. When it hit the peak current, then switch turns off. Now, we want to obtain the average value of this inductor current. That means this is my average value of the inductor current, and this average value of the inductor current we can simply take this average itself, that means this point. Okay. So, one approximation we can directly compare this approximation, and if we do that, then what is this point? That means let us take this point is 1. What is this point? this point nothing but, if I take this peak value, because value is something which is not in our hand, but we want to find out average current in terms of the reference current, which is like actual control current coming minus the ramp. So, this is my actual reference current, which is compared with the inductor current. So, I want to obtain the average current in terms of the reference current as well as the current ripple. So, this can be obtained that this IC, this point, that means this point, IC minus MC dt, which is the value here, minus this half of this ripple, minus this half of this ripple, and this is exactly find the average inductor current. So, it is nothing but this value, and this is nothing but the point which is number 2 point. So, this is my number 2 point coming, and this is half of the ripple, right. So, the number 1, the average inductor current I am getting from here, I am taking the number 1 point is my average inductor current equal to number 2 minus half of the ripple. And then what is the ripple expression? During this particular duration, it is m1 into dt, that is my current ripple, and that divided by 2. So, this is the expression. Now, once we obtain this current average expression in terms of this, if we rewrite, then what we have to do? This is my average dynamics, and in order to get perturbed linear model, we have to replace this average quantity by the steady state quantity plus perturbation. That means, I need to replace my average inductor current by steady state inductor current plus perturbation, then average control current which is coming out of the controller, or it is a current fixed current reference, or it can be a output of the controller, or it is just a control that we are sending from the outside. That means, it is the, if there is no ramp compensator, this is a peak reference, but now along with this current, control current, we are subtracting the reference ramp slope, that means compensating ramp. So, it is the DC value and the perturb value. Then the duty ratio can be replaced by capital D, D perturbation, and the rising slope, we are only considering rising slope, can be written as the capital value, that is the steady state value, and its perturbation. Then we want to obtain perturb value. So, if you go back, so we will consider only perturbation, that means here it is IL plus IL perturbation. So, this is my quantity. Then what about this quantity? It is my IC plus IC perturbation, right. Then for MC, it is a slope of the ramp which is fixed. So, we are not taking any perturbation in the ramp slope. Then we can write D to be D plus D perturbation, right, and then we can write this term, we can write m1 dt by 2. That means, if we consider m1 dt by 2, we can write m1 plus m1 perturbation, then capital D plus D perturbation T by 2, and this can be separated like m1 dt by 2 plus, now there are two terms, one is m1, okay. So, that will find, that means what is this? m1 d perturbation T, m1 T by 2 d perturbation plus dt by 2 m1 perturbation. However, we are ignoring, that means there is one more term which is m1 perturbation d perturbation T by 2, but this we are ignoring, we are this is negligible, because for small perturbation this is negligible, otherwise this will introduce a nonlinearity. So, we have to obtain perturbed linear model, then you separate out the DC term, we ignore the nonlinear term, then you will end up with only the linear term, and then That means this is the equation which is very important, that you should keep in mind. Now, what you have to do from this equation, our objective is to write D as a function of IC tilde, IL tilde and M1 tilde, and there are other constant parameters. So, part of current or after that. So, this is the expression that we are looking for, and this is the modulator gain. And what is this? This modulator gain is nothing but this term, 1 by this term, right, 1 by this particular term. Another approach, method 2. So, here in the first approach we took the average current. If we go back, we took the average current as point A. So, point A we have taken as the average current. But now in another scenario we can take the average current. So, this was my point 1 now, and this was our point 2 in the earlier case, and now we are considering an additional point to be 3. So, what I am considering now here, my average inductor current over a cycle T is my average inductor current for the duration dt So, I want to take the average inductor current during the dt plus the average inductor current due to dt dash t, that is 1 minus dt. But now we are taking 2 points and their weightage is, this is my dt and this is my d dash t or 1 minus dt. So, in this case we will take simply d, that means if we take 1 by t, so this will be my dt and this will be d dash t and the bracket close, and that means it will be d into IL dt plus 1 minus d into IL d dash t. Okay. So, I think it is not feasible. So, let us take it, or you can write in terms of d dash into IL d dash t, and all these case we are writing d dash to be 1 minus d, and this is exactly writing. Now, here the point 2 remains same, which is nothing but IC minus MC into dt. So, that means if we write again, ILT is that average, and what is ILDT? That means if I go back, ILDT is nothing but this point 1, the current at point 1, and what is, that means I will say my ILDT, this particular term is nothing but this point, and if I take this point is nothing but my point 3. Okay. So, average if we take, then we can get that ILDT, which was our earlier equation. Then we are taking an extra term. Then what we are doing, that means extra term means this is my at point 3, it is my point 1, and this quantity in all case is my point 2, corresponds to point 2, because this point is same. So, then average inductor current we can write after this substitution. That means if we substitute this into this and this into this, then we will get this complete equation. Then again we apply perturbation. We can simply apply Taylor series. That means, in this expression, suppose if I get, it is very easy to get, suppose if I get IL perturbation is a function of IC perturbation, sorry, M1 average. So, I can consider this to be average, then D, then M2, then I can obtain IL tilde to be dou F dou IC into IC tilde plus dou F dou M1 into M1 tilde plus dou F dou M2 into M2 tilde plus dou F dou D into D tilde. So, what is this term? This is simply nothing but IC. You see, this term is coming nothing but IC because it is 1. This term is simply 1 equal to 1 because I am taking this whole term to be F. So, if we differentiate with respect to IC average, I am talking about this is average quantity, then you have only term here and coefficient is 1. So, it is 1. So, it is 1. Now, if we differentiate with respect to suppose if we respect to M1. So, if you differentiate with respect to M1, then you will get D square, then you have to substitute steady state, all substitution steady state. At steady state we are finding, right. So, from this equation if we write what is my dou F dou IC average. So, this is simply 1, right. Then what is my dou F dou M1 average? So, you will find only this term has this. So, it will be and calculated at steady state. So, it will be d square t by 2, d square t by 2 and this is the term, the coefficient d square t by 2. Okay. So, this into M1 part of. Similarly, this all average quantity we have to differentiate. Otherwise, you can simply substitute d equal to let us say capital D plus D tilde. You can solve that, but this is much easier way to do that. Now, if you do what is my dou F dou D? So, you will first guess this term. So, minus at steady state minus MC, although MC small MC large capital they are same because we are not perturbing it, into T because we are differentiating with respect to D. Then for the second term like this term what we will get? M1 dt because there is a D square term. So, if you differentiate 2D and D should be capital because we are finding at steady state 2D, 2 to get cancelled. Then if you take this term what you will get? You will get minus. So, I think there should be plus, no minus, fine. So, minus M1, that means we are talking about now minus because we are talking about this term we are talking about minus M2 T and there is a square term. So, it will be 1 minus D and square means 2 will come out. So, 2 to get cancelled. Now, we have to differentiate with respect to 1 minus D. So, there will be plus sign into T. That means, it will come as this term. So, it will be M2 1 minus dt that into delta this term. So, this whole term will come, all term will get it, right. So, the part of dynamics can be obtained by applying partial derivative as I discussed. Then you can get all this delta d term. Fm is the modulator gain. What is Fm? So, it turns out to be because at steady state M1 dt, that means if you take the steady state inductor current, this is my d into t and this is my 1 minus d into t, right. So, if I take the steady state rising slope M1 and falling slope minus M2, then the inductor current ripple at steady state is equal to M1 dt and it is also equal to M2 1 minus dt. So, that means this to M1 dt is equal to M2 dt, and if you that, then this term actually will be 0. This term will have no contribution because these two will cancel each other. So, you will get MC. Now, in a buck converter, it is a buck converter only. I mean, if you take a buck converter, M1 is my Vin minus V0 by L, M2 is V0 by L. So, I can take M1 perturbation is nothing but 1 by L into input voltage perturbation minus output voltage perturbation. M2 should be output voltage perturbation by L. So, the overall small signal becomes Fm into IC perturbation, IL perturbation minus K1 into V minus K2 into V0, and all this we are writing from here. Okay. So, then if we tabulate, so under first method your Fm is this, and under second method your Fm is this. Then K1 can be obtained by first method this, K2 is this, and for the second method your K1 is this and K2 is this. So, this can be obtained whatever we have discussed so far, and this is a basic equation. Now, we can plug in this equation to our original AC equivalent circuit model. That means, if we recall that when we derive the AC equivalent circuit using either average switch model or circuit averaging technique, then the AC equivalent circuit, there was an open loop duty ratio perturbation was there, right. So, now if I am going back, this is my AC equivalent circuit that we have discussed earlier. They have already discussed earlier. So, in this circuit, the perturbation, the duty ratio is the one which is coming from the closed loop, and this expression we have got from our this expression. Okay. So, this we have just plugged in. That means, D perturbation is Fm into K1 in bracket minus K1 into V in perturbation minus K2 into V0 perturbation minus IL perturbation plus IC perturbation, and if you see, yes, only IC perturbation and all are minus. Here we are considering Z1, which is the impedance of the inductor plus its equivalent resistance, and equivalent resistance consists of inductor DCR plus switch RDS on, all are included, and then Z0, which is the output impedance, because we know for approximate small signal model this branch becomes the output impedance, right. So, that we are writing output impedance, and if we look from this side of the converter, then the input impedance is nothing but the RL circuit that is in series with the parallel combination of this Z1 Z2. Now, if we want to get the accurate small signal model, if we obtain IL perturbation, that means we want to obtain this current IL perturbation, and let us consider this whole branch as an impedance, and this impedance is nothing but my Zin impedance. That means, and if we do not consider any load perturbation, that means, and if we draw this circuit, that means if you draw this side here, we know that if we this current source, that means it can be vanished and we can remove because it is across a voltage source, it has no meaning, and this voltage source if you map to this secondary side and with a step down ratio of 1:D, then you can draw this circuit like this. So, this is our so we have one source here, that means this is our V in D into V in, which is the mapped one in this side, right. Then it is series with V in into D perturbation, and this has an overall impedance of Z1, Z in, and this is my current expression. So, my inductor current will be sum of these two voltages, which is here, divided by the impedance. Now, if we rearrange, we take D by Z in out, because we want to arrange in a way. So, input voltage plus this. So, this is just a rearrangement from this stage to this stage, but this stage was important. Now, you will see we can write the inductor current, if I write, that means it is like this. So, you have an input voltage perturbation which is summed up, and this side we are getting something like V in by D, and this is our duty ratio, and this multiplied by D by Z in is my IL perturbation. Okay. So, this is exactly that. So, we talked about this branch, Then how are we generating D perturbation? It is Fm into minus K1 into Fm in bracket. That means we know that D perturbation was Fm in bracket IC perturbation minus IL perturbation. So, it is added here, this is subtracted, then minus K1 into V in perturbation minus K2 into V0 perturbation. So, this is K1, K2 that we have discussed. And then IL to V0, if you go back, so this is my IL, that means this current is my IL perturbation and this branch is my Z0. So, then what is the voltage across this branch? This branch voltage is nothing but current multiplied by this Z0, impedance, and this is the Z0 impedance. Okay. So, you can write IL perturbation in terms of this. Now, we want to find out that here you can see two loops. One is the inside like a voltage loop, right. In that case, let us forget that current loop for the time being. We are only talking about the voltage loop. If you remove the current loop, then what is there in the voltage loop? That means if you start from the number 1 and move along this path, right, and come back, then what is there in the voltage loop? So, it starts with Fm is there, V in by D is there, then V in by D into Zn. So, dd get cancelled. So, Zn is there, V in is there, then K2 is there, and so here Z0 is there, it is a voltage loop, right. So, this is clear. So, voltage loop gain is clear. Once you obtain the voltage loop gain, now then you have to obtain the current loop gain. Okay. So, what are we going to achieve? Now, it looks like we have started from this point, right. That means we have started from here, we are ignoring, that means we are ignoring, let us say, equal to 0. So, that means we can simply remove this path. We are not considering the perturbation in the input voltage for the time being. Now, if we look at this point to this point, so this to this point is nothing but what? So, if we look from IL, that means IL by I1. So, that means we start from journey here, we are going like this, and then okay, so first I want to obtain this V0, that means I want to obtain what is my I1, that means what is my this point, forget about, that means this is my number 1 point. So, that means what I1 we have already obtained the voltage loop gain TV. Now, once we obtain voltage loop gain, then for the voltage loop point, that means this is the current loop. So, what is my, okay, first let us find what is my V0 to IN, that means this is my V0 and this is my I1, that means 1 to 1 dash. What is there? So, you see this path contain everything forward path except for K2, that means I can write it is 1 by K2 into my voltage loop by 1 plus voltage loop, right, because it is nothing but the expression between this point and this point is nothing but I want to get forward path divided by 1 plus loop, voltage loop, and the forward path has the voltage loop gain, I mean transfer function but excluding this term K2, that is there, but it is now it is in the feedback path. So, you have to write 1 by K2 into TV by 1 plus TV, right. Now, we want to obtain what is my IL to I1. It is nothing but IL to V0 into V0 to I1, right. Okay, so let me write here. That means we want to obtain IL to I1, which can be written as IL to V0 into V0 to I1. What is IL to V0? This term, that means it only this impedance will come, that means it is 1 by Z0. So, this is the term. Then multiplied by what is V0 to I1? So, this we already saw, it is 1 by K2 into TV plus 1 plus TV, right. So, it will become 1 by Z0 K2 TV plus 1 by TV. So, this is what the expression. Next, once we get, that means this is now my current loop. Now, what is my current loop? Now, my current loop, that means I will start from the loop, that means I will start from this point, number 2 point, and I want to come back, I start from this point, number 2, and I want to come back to this path. This is my current loop, right. So, this is my 2 dash. So, that means what is my current loop transfer function? It is nothing but the one which is obtained, because we have not considered any feedback gain in the current loop. If we consider, then they will be different, otherwise this is the one which we obtain IL theta by I1 theta. So, that means we got the current loop gain. Now, what is my IL by IC? So, in IL by IC, that means now we are talking about the number 3 point and number 3 point dash. So, we are getting between 3 to 3 dash, and this is nothing but the forward path has everything, which is the current loop transfer function divided by 1 plus current loop transfer function. So, this is the transfer function. Okay. So, once we get current loop transfer function, then we have to get what is my control, because our ultimate control to output transfer function is V0 by IC. Okay. And this can be obtained as V0 by IL into IL by IC, right. And what is V0 by IL? It is Z0 into, and what is IL by IC? It is Ti by 1 plus Ti, right. And that means my GVC is equal to Z0 into Ti by 1 plus Ti. So, this is my current loop gain. If my current loop gain is very larger than 1, then GVC will approximately become Z0, and this is nothing but our control to output transfer function in case of the approximate model. So, both the model will match once the current loop gain is very high, but if the current loop gain start decreasing, then there will be a significant mismatch in the model, and that we will see. Another thing, the natural sampling effect, where in the Brown and Middlebrook thesis, it was reported that if you take any perturbation in the inductor current, that means if you consider a nominal inductor current, this is my nominal inductor current and this is my nominal current reference minus the ramp slope that we have discussed, right, which will be compared to the inductor current. Now, the current reference is perturbed, so it is shifted up. Similarly, your ramp slope, the whole thing will get shifted up, and inductor current is also perturbed, there is a perturbation shifted up. Now, due to this perturbation, you see there is a change in the sample inductor perturbation. That means if we obtain the IL plus IL perturbation minus IL, that means this is the part of inductor current, the original. So, there is an initial perturbation. So, this IL perturbation during the nth cycle, that means we can say this is my NT, this is my N plus 1T because switching cycle. So, during the nth switching cycle, this perturbation will be reflected because we have part of the initial current of the inductor current, we have also part of the current reference. So, there will be a perturb current, and that perturb current will remain same till it hit the next time when it hit the reference current, that means the reference current minus the RAM like a sawtooth waveform or basically RAM compensation. So, this is the overall current reference, and this indicate, that means it only changes when as if it is almost after one cycle it is changing. So, this is like sampling and hold behavior, sampling effect. This is naturally present in even analog current mode control. And then this current mode control, if you want to investigate, you need to include discrete time model. Generally it is discrete time model is used, or you can say sample data model. Data model. So, sample data model means it is we are modeling between the two sampling instant where as if these two are the sampling instant. But the discrete time one is more generic one, that means discrete time, your time period, the sampling time can be smaller than the switching period and so on. Here we are making like there is no actual sampling, it is like a stroboscopic or the virtual sampling just to create a model of the system, right, sample data model. But then Ridley actually incorporated, that means this sample data model if you incorporate and if you obtain the continuous time model, then in our earlier model which was there, you can get a current loop transfer function. In the current loop there is a sampling transfer function will come, and this effect is coming due to a sampling effect, and we are not going to derive or discuss this in this course because this is left as an advanced topic, but this sampling effect can be included. And if you include the sampling effect, then the control to output transfer function will be written like this. This is like similar to our first order pole with one ESR0 one pole, that means this one, and this is due to the sampling effect, okay. And this model is used almost most of the industry, they use this model, but still this hold effect has a second order pole like a 2 pole and the 1 pole. So, we want to see if we use our first order model which is very easy to design, then we want to compare what happened with the Ridley model, okay. So, that means we want to do a comparative study using approximate first order model, more accurate model as well as a Ridley model for getting control to output transfer function. And then we want to validate using reference transient which is linked with the closed loop bandwidth, and then we want to consider with and without RAM compensation using Matlab case study. Let us go to the Matlab. So, in this Matlab we are talking about the model comparison, that means here all these codes like a parameters. So, initially we are talking about 12 volt input, then we obtain whatever transfer function we have written so far, this is a Matlab code, that means all duty ratio, M1, rising slope of the inductor current. I am operating initially let us say 1 ohm resistance, then switching frequency is 1 by T, the time period is 2 microsecond, then R equivalent is RL plus R1, R1 is the on state resistance of the inductor, okay. And the K2 I talked about, K2 corresponds to the V0 feedback loop, that if you go back to the this transfer function. So, we have talked about K2. So, K2 is this particular term, we are talking about this particular term, okay. So, now let us go back K2, then this is my Vm is the amplitude of the RAM, that means if we use a RAM it is varying from 0 to Vm maximum voltage, and the modulator gain is simply 1 by Vm, okay. And if you take the slope of the compensating ramp, it is nothing but Vm by T, because it is varying from 0 to Vm for a timing periodic interval of T, time period T. And this is my ESR 0 and this is my pole that we have discussed, okay. Then open loop output impedance we have discussed. For using first order model, we have discussed the control to output transfer function. This is nothing but same as the output impedance. So I have written GVC1, it is the control to output transfer function using method 1, which is the approximate model. Now for the accurate model, then we obtain ZC, Q0, Q, we obtain numerical, because whatever model we have discussed using accurate model means I am talking about this, all this derivation we have considered, input impedance and all these things. So with this we have discussed that we have ultimately obtained this control to output function here. So this is our expression we are talking about. We want to obtain the control to output transfer function using accurate model here. So for that we need to derive the current loop transfer function, voltage loop transfer function first, then current loop transfer function, then GVC2, that is the control to output transfer function using accurate model. Then we are talking about the Ridley model, where alpha, everything is whatever as per the equation that we have discussed, like if we have discussed this equation we have considered. So this is a Ridley model, okay. Now we are designing the type to comp. So design we will discuss in this course, in this lecture later. But suppose I have designed the compensator using just a first order model, and then I have certain objective. I want to achieve a desired bandwidth, let us say 1/10 of the switching frequency. So 1/10 means, so if it will ask for what is my crossover frequency, I will set 1/10. That means 500 kilohertz is my switching frequency, I will set 50 kilohertz. Then it will automatically generate, I am using a type 2 compensator. So what will be compensation? I will discuss about this part. Then it will draw the loop transfer function. So same compensator is used for all three transfer function. That means the approximate one, then accurate one and the Ridley model. Then it will draw the Bode plot of the loop transfer function. Then we will obtain the closed loop transfer function using 3 method, and then we will get the transient response of the using 3 different model. That means we will take the transient response, we will say the reference transient response. It is changing from 0 to, that means we are applying a reference step of 0.1. So it is changing from 1 volt to 1.1 volt at 3 millisecond duration. So all this we have discussed in voltage mode control itself, how to match the model. So here we are getting the step response of the closed loop system for all three cases, and for the first case method 1 we are using red color, for method 2 we are using green color, and for Ridley method we are using blue color, and actual switch simulation we are using magenta color. So let us run and see what happened. So it will ask for ramp voltage. Let us say we are setting a very low ramp voltage 0.001 and we will run. It will ask for bandwidth. So let us say 50 kilohertz is my bandwidth. Then it will design. So I will go one by step by step. This is my transient simulation matching. So let us go back. So the magenta color is the actual switch simulation that we are getting from closed loop, and if you go back to the closed loop, that means I have a buck converter which is implemented closed loop implementation. So this is my buck converter, I am calling it, and I am using, there is no, so this is my RAM, so I need to use RAM. This is my inductor current. This transfer function I am getting from, I am plugging from the Matlab code, but here there is a provision for load feed forward, but I am not adding yet. Okay. Okay, next. So this is my Matlab model. Okay. Now I am just once more I am running. So it will ask for ramp voltage, and let us see 50 kilohertz bandwidth. So you will see that the red one is coming from my first order model, and which is, there is a slight mismatch in terms of ripple voltage, otherwise it is matching. Green one is coming from the accurate model, okay, and the blue one is coming from Ridley model. So if you see we are interested in this part, that means we are interested in this particular part. So, all these 3 models are matching more or less fine, only and if you wait for a long time, they will eventually merge together, all 3 models will actually merge together. So, they will merge together, all 3 models are there. Okay. So, you can see there is a green color trace is there. So, they will merge together, but there is a slight difference in the transient performance, but that is fine, and here we are running at 12 volt. Okay. So, 12 volt input and 1 volt out. Now, I want to see what happened in the same condition if we add a ramp compensation. First, let us see what happened if we want to increase the bandwidth to 1/5 rather than 1/10. So, again we are using very negligible amount of ramp because 12 volt to 1 volt does not require any ramp, and now we are going for 100 kilohertz. So, we are trying to push the bandwidth and we want to see how fast. So, you see none of the model actually capture this behavior actual switch simulation, because in actual switch simulation there is a huge overshoot, because the model is not valid. I mean it is inaccurate when you try to push the bandwidth at close to 1/5 of the switching frequency. That means we should not try to do that. Another way, if we try to increase, let us say 0.001, let us say our 500 kilohertz is my switching frequency. So, I want to obtain 500 divided by, let us say 8 times, instead of 1/10 I will 1/8, and let us see how far they matches. So, 1/8 they matches somewhat better, that means we can push a bandwidth a little higher, like a 1/8 in voltage mode control we got 110. So, in current mode control we can go like 1/8 or so, right, the bandwidth, and you see the model they are matching reasonably well. Now, we want to see what happened if we want to add a large ramp. So, we want to now consider the ramp is, we have used a overcompensated ramp for 10 volt I am giving ramp when it is not required, but I want to check whether the model is valid or not, and 50 kilohertz is my bandwidth I am setting. Now, I am trying to match. You see that the Riedle model is matching fine, okay, and the first order model matching fine with slight mismatch, but Riedle model is more accurate, but first order is also good enough, but accurate model is not matching, because if you go back and if you check the accurate model, you see the current loop gain, if you consider the current loop gain in this expression, the current loop here, because it is TV by TV. So, even if we ignore this effect in the current loop, FM will come in the forward path. That means the current loop can be approximated as if this K2 is set to 0, then the current loop can be written as, the current loop transfer function is simply FM V in Z in, right. So, if your, and what is FM? It is 1 by Vm. So, if you take a large ramp voltage, then 1 by Vm is small, so that the modulator gain is small, and if the modulator gain is small, then the current loop gain decreases, and if the current loop gain decreases, then our discussion here, so this approximation does not work. That means, if I take this approximation, this does not work, because current loop gain is coming close to 1 and you cannot ignore. So, there is a significant deviation between this and this model, and that is why, because here this model, the modulator gain is simply 1 by Vm in this method 2, accurate method. That means this method, that is why there are so many model in current mode control, because that fundamentally differ in terms of modulator gain. In case of Riedle model, the modulator gain is basically, it is the, so in case of Riedle model, so if I go back, Riedle model, modulator gain was like a FM was taken as MC plus M1, MC is the capital MC, into T. That means it is both the addition of the slope of the ramp, if we add it, and this is because, what was the analogy behind this? The analogy behind this, that if you take a peak current reference, and this is my peak current reference, this is my control current, and if you consider inductor current, right. So, we can take the inductor current slope M1 is like in voltage mode control. So, what we do, we just take this slope of the ramp 1 by MC into T is my modulator gain in voltage mode control. So, here the analogy is that if there is no ramp compensation in this method, Fm is simply 1 by M1T. That means as if it is like a voltage mode control, the ramp is replaced by inductor current. So, the slope of the inductor current will act like a slope of the ramp. So, which is consistent, logically consistent. But if you add ramp, then as I told, if you add ramp, then the overall current slope will be inductor current rising slope plus ramp slope, and that is exactly what is happening. So, that means this model even, but if you consider the accurate model and this model, even the modulator gain is decreasing because we are adding ramp plus supply the ramp of the slope of the rising slope, but still matching is quite nice because it includes the sampling effect. Okay. So, that means we can conclude that even with ramp compensation, our first order model is reasonably fine, but the Dirichlet model is more accurate because of the sampling effect. And so, that means we consider all, and what are the recommendation? So, we can design using first order model. If there is no ramp compensation, this is perfectly fine. If we consider ramp compensation, we still can design it, but we should validate for both cases with Dirichlet model for frequency response matching as well as the transient response that we have checked, the response coming from the transfer function like AC analysis plus DC offset, and all should be checked with actual switch simulation, and all we have done, right. So, the final recommendation, we can simply design the current mode control using first order model. Now, with this, the control to output transfer function, we want to design current mode control. So, the current mode control, now we are designing with a first order model. So, this is a control to output transfer function, then we are designing a compensator, and this is my loop transfer function. So, what is the loop transfer function? It is a product of the control to output transfer function into the controller, and this is my control to output transfer function for the first order model, and we know all this expression already we have discussed. Now, the loop gain analysis. So, we want to design this compensator and we want to shape the loop. So, what should be the structure of the compensator? It depends on number of poles and zeros. So, we have 1 0 1 pole. So, the first thing, we have a ESR 0 which is located at high frequency, and we can cancel by using a controller pole. We have a single real pole, and which actually make the response slower if the load resistance is high, and at DC we have to also at DC gain in the loop transfer function, the DC gain is a load resistance dependent. So, it have a pole load regulation. So, the primary loop shaping objective, we want to cancel ESR 0 by considering one pole in the controller. We want to cancel single pole by considering a 0 in the controller. So, controller require 1 0 1 pole, and then we need to introduce one integrator because we want to reach 0 steady state error or very reduced steady state error, and the primary loop shaping objective, and then we have to set the compensator gain DC gain to meet desired frequency, crossover frequency. So, a type 3, that means we need how many poles? So, we need 1 0 and 2 poles, 2 poles, that means with including the pole at origin. Okay, that means type 2 compensator is needed. Type PI may be sufficient if there is no ESR 0, because that we do not need to cancel. So, for an ideal buck converter, or if the ESR is very low, which is going far away, if the ESR goes beyond much beyond our control bandwidth, or even it is go close to the switching frequency, then simple PI controller should be enough. That is why in current mode control people use either type 2 or PI. So, they will be more or less synonymous if the pole of the type 2 compensator, one of the pole which is used to cancel the ESR 0, it is placed much high frequency. So, that effect is negligible. That means, we need a type 2 compensator. If this pole is kept far away, then as if this effect is negligible, then this can be approximated as a simply Kc 1 plus S into omega Cz by S, and this is the structure of a PI controller. This is a case when the pole of the controller is placed far away and which is used to cancel the ESR 0 if the ESR 0 is left far away, right. So, our condition, the controller 0 is used to cancel the pole of this plant and the controller pole is used to cancel the ESR 0. And if we write the loop transfer function, it is R Kc, because if you go back, if you cancel this and cancel this using the controller, that means if we cancel this with the controller this pole, and if we cancel this using controller 0, then you will have this term and this term. So, this is nothing but our loop transfer function, and if we write the frequency response by replacing S equal to j omega, then you can separate the real part. Real part is very simple and imaginary part is only at the denominator. So, you will get a phase of minus 90 degree. So, we are getting a first order system. Loop transfer function is a first order which have a minus 20 degree per decay, the gain. It is just simply straight line, gain will start falling like minus 20 degree per decade. Okay. Now, we need to select what will be my crossover frequency. So, at crossover frequency, our gain should be 1 and this gives us the controller gain is simply omega c by r, and then phase margin is always 90 degree. So, we need to close loop set. So, we have to select the suitable crossover frequency. Now, let us go a Matlab case study. Here we are talking about, now we identify the first order model is good enough. So, now we will go for the first order model. Now, we want to make load transient. That means, here we are initially it is 1, that means 1 ohm resistance, 12 volt input, it is in the parameter file. If you go to the parameter file, input is 12 volt, I can take it out. So, I can keep input voltage is 12 volt, reference voltage is 1 volt, initially load resistance is 1 ohm, and all this derivation we have discussed. So, the compensator is designed using the method I have discussed. Then you can draw the loop transfer function and then it will plot the, we are making the load transient response. So, it is a 20 ampere load step we have applied. Okay. So, if we run it, it will ask for bandwidth. So, if you set 50 kilohertz, then let us go and check. So, you can see the loop transfer function clearly shows that, it is just an integrator like a some gain by S, so it is falling and your phase is minus 90 degree. So, phase margin is 90 degree, and if you go to the response of the output voltage, so there is a ESR jump, that is why model is capturing that ESR jump, and then it is accurately capturing the behavior of the closed loop system under load transient response, is more or less capturing. So, you can predict what will be my undershoot, overshoot and so on, right. Now, if you want to increase the bandwidth, if we again run it and if you want to increase, let us say 1/5, that means 100 kilohertz is my crossover frequency, you see the model start diverging, because your actual switch simulation you have a huge peak which cannot be captured by your model, because the model will not be valid. So, again I have told that you can select that, let us say 1/8 will be good number. So, 500 divided by 8 may be a number. So, that means 1/8 can be a good choice and it matches reasonably well. So, in current mode control you can slightly increase the bandwidth and that it become 1/8, okay, slightly, but still there is a mismatch. So, I think 1/8 to 1/9 or I can say 1/10 is the perfect thing that we are working. So, we have seen that response of the current mode control. Now, that means we have discussed open loop impedance. Now, the output impedance. So, current mode control, one of the problems is the load current feed forward, is a very slow transient response in load transient response, and if you want to increase the bandwidth, then the model is not valid. So, it is sluggish because it is approximately like a first order overdamped system. So, if you want to speed up the transient, what you can do, you can simply incorporate the load current feed forward. That means, instead of a ramp, I can simply add load current feed forward, because the load can be added with the this reference current, or it can be subtracted from the load inductor current. That is why -1 gain is given. So, now if we run it with 50 kilohertz, so I have now added the, but now the match closed loop response will not match, because in the model I have not considered this So, let us remove this, because we have not discussed this part. So, this will match fine, that means I will comment it, I will run it again 50 kilohertz. So, the response will be very fast when you talk about load load current feed forward. It can be significantly improved over without load current feed forward. Okay. So, the load current feed forward, if you consider, then as if we are adding this load current with the reference current which is coming out of the controller, or we can subtract from the inductor current, right, we can subtract. So, if you do that, then we can write that V0 expression in terms of Z0 into this IL minus I0, and what is IL? It is nothing but GIC into this current plus this current, plus this current. So, this is this current, and then if you further substitute, what is this current is GC into, because we are not talking about in load transient, not talking about the reference change. So, it is 0. So, your I1 dash is nothing but GC into minus V0 perturbation, this product. So, that is written here, and if you write the complete thing, you will see this is a loop, this Z0 IC GC, this whole product is nothing but my loop transfer function. So, loop, and if you write the complete equation, then this is the final expression, and what is the output impedance of the closed loop system? Minus V0 by I0, and this will be simply this. Now, we know that GIC, which is the transfer function between IL and IC, right. So, in approximate first order model, this will be approximately equal to 1, because in our first order approximation, we have considered the inductor current perturbation to be equal to IC perturbation, and if it is so, then this will be simply 0, because this term will be 0. So, in approximate sense, it shows that closed loop output impedance is 0, that means it behaves like an ideal voltage source, but in practice there will be slight change, because that will come due to the dynamics of the current, because your inductor, in order to achieve 0 output impedance, your inductor has to be negligibly small, almost 0, and output capacitor has to be very large. So, in order to achieve this, your characteristic impedance, which is nothing but square root of L by C, should be tending to 0, it should tend to 0, and this is practically not possible, because neither you can reduce the inductor below a certain value, your current ripple will increase, nor you can increase the capacitor significantly, because it will penalize your power density, right. So, it is like this. So, that means the closed loop output impedance can be, whereas the open loop output impedance is a function of load resistance, but now the closed loop output impedance virtually become close to 0. So, there is insignificant, if there is a load step transient, the output voltage as if there is no change, and this is in average sense it is more or less correct. That means, if you take very closely, if you see only except for this because this is due to the finite slew rate of the inductor and capacitor, because inductor current is rising, it cannot reach immediately, because if you go back here, if you just open up, as I said that it takes time, right, inductor takes time, it will slew up. So, slew up, and if you reduce inductor value smaller and smaller, then this will be reduced even become smaller and smaller. So, that means, if you go back to our power stage design, if I can reduce my inductor value, that means if I go to my buck converter parameter, if I take a smaller inductor, let us say I am just taking 0.1, the ripple will be quite large, but let us say if we run it 50 kilohertz, then you will see the output has almost no effect, right. So, you will see that output will have almost no effect, that means it is virtually become 0, in negligible effect, that means it is in the order of some 5 to 10 millivolt or 20 millivolt, but the penalty for such a small inductor, your current ripple is significantly large and which is not acceptable. So, that means it is not exactly 0, it is close to 0, the effect is neglected. So, in summary, we have discussed the comparative study of various modeling technique, then we did model validation using different small signal model, and we validated using Matlab simulation, and we have discussed that which model should be used for the design, and then we also discussed the loop shaping objective as well as the design of current mode control in a buck converter. Then we have discussed the closed loop output impedance with load current feed forward. Okay, so with this I will finish it here. Thank you very much.